what others? Is it? Yeah, is it this topic you wanted? That
Yes,
is about. Huh?
yes,
So
sir.
which is not recorded. This one. Okay.
Yes.
Okay. Just let me first of all say what is this spread spectrum communication system. Okay, actually basically it is developed for military communications, okay, to have secure communication. Okay, it is originally developed and used for the military communication. Okay, and other than military, it is also used in civil applications like digital cellular communication. Okay, like that is CDMA. Okay, even it is used in cordless telephone and other wireless communication systems like inter-office wireless communications and all. Okay, so why especially they have started adopting this in militaries because this spread spectrum provides more resistance to the jamming. Okay, means it is possible to hide the signal. This spread spectrum signal is possible to hide by transmitting it at very low power. Okay, so that signal will become very difficult to identify by the unintended listener. Okay, in the presence of noise. So in that way, we say it has a low probability of intercept. Okay. So because of these two reasons, it has been used in the military, and later on it has been used in the commercial applications like civilian applications. Also, I said okay. So the idea here is the information signal is basically a low frequency signal. Okay, it occupies very less bandwidth. Suppose if I wanted to say or give an example of voice signal, see, I used to say it exists from 300 hertz to 3400 hertz, right? So that frequency band is very small. So what we do here is, in case of spread spectrum modulation, we spread this information signal over a wide bandwidth. Okay, so we call that as chips. Means we multiply this information signal by a unique pseudo-random code. Okay, that pseudo-random code that depends whether it may be 8-bit or 16-bit or 32-bit. So we can increase the complexity. Even we can increase the length of the pseudo-noise code. Okay, so depending upon that, we will be able to spread this information signal into small chips over a wide bandwidth. Right. So at the and we can do modulation. Then we can transmit over the channel. So at the receiver side, the user, whoever is having the same pseudo-noise code, right, or whatever the pseudo-noise code which is used at the transmitter side for transmitting the information signal is used, no? The same pseudo-noise code should be there at the receiver side also. Only that user will be able to recover back that information signal. Okay, for other users it becomes a noise. Okay, so that is the idea of this spread spectrum communication. I hope you could catch this point.
Yes, sir.
Conventional normal communication system, what we do is we don't spread the bandwidth of the information signal. So we just do modulation and we send it. But here, what happens in case of spread spectrum, we use a unique code. I said that. Right? That what is that unique code? That unique code is the pseudo random code, pseudo noise sequence, right? So that code will be multiplied with the information signal. Then we do the modulation. Okay, so when we multiply the information signal with the pseudo noise code, we say that process is known as spreading. Okay, spreading of the spectrum of the information signal. Then we do the modulation. I said the most widely used modulation technique is BPSK, and another one is FSK, right? So BPSK is used in direct sequence spread spectrum, and FSK is used in the frequency half spread spectrum. Actually, there are two types of spread spectrum. I said one is direct sequence okay, spread spectrum system, that is DSS, okay, direct sequence spread spectrum system. And second one is what I said, frequency hop spread spectrum system, right? In case of DSSS, we use BPSK as the modulation technique. In case of FHSS, we use FSK as the modulation technique. Okay, so to say about this spread spectrum, I said it is developed and used for the military communication because of what reasons? Because it can provide high resistance to the jamming. That is the first point to be noted. And second thing is, it is possible to hide the signal, okay, by transmitting it at low power. Okay, so at the receiver side, it becomes very difficult to listen or detect by the unintended user. Okay, it almost looks like a noise for the unintended listener. So that is why we say it has low probability of intercept. With that, we can say it is possible to have more secure communication. Okay, so because of these two reasons, it has been adopted in the military. So later on, it has been used in the civilian applications. As one such example, I said it is used in CDMA, that is 2G and even as well as 3G cellular communication. Okay, just to say what is the spreading process, I've given here an example. See, this is my information signal having a bandwidth of B, right? So the spreading process is nothing but a multiplier. Okay, and here I am applying the spreading code. That what is the spreading code? Spreading code is the pseudo noise code. So if I multiply these two, I will be getting a signal with a bandwidth which is much higher than the bandwidth of the information signal. So this is what we say. Then we do modulation after this. Okay, so what I would like to say is it is a type of modulation, means this spread spectrum, right? In which the modulated signal bandwidth will be much greater than the message signal bandwidth. So I think it is very clear with this picture, no? Because here I said the information signal having a bandwidth of B, which is multiplied by a pseudo noise code, right? This pseudo noise code, I said it varies. Okay, I can use 8-bit, 16-bit, 32-bit, 64, depending upon that application. Okay, so that will be multiplied with this message signal. No? So with that, I will be able to get a signal which is having very large bandwidth compared to the message signal. So that is what the thing here, what I said. Okay, so spreading of the message signal spectrum is done by spreading code called the pseudo noise code, right? And that this pseudo noise code will be independent of this message signal. Okay, there is no relationship between this pseudo noise code and the message signal. Means it does not depend. Pseudo noise code does not depend on the message signal. Okay, it is, these two are completely independent. I hope it is clear. At least now we will be able to say what is spreading process, just to understand. Yes, is it clear?
Yes,
You
sir.
should say yes or no.
Yes, sir.
Okay. Fine. Then, so let me take up the spread spectrum communication system block diagram. So I think, as I said, I think I stressed it also while explaining this. This will be asked in the exam for 6 marks, like that. They will ask you to explain the spread spectrum communication system with the block diagram. So we need to understand in what way this block diagram is different from the block diagram of a normal communication system. Right. So in a normal ordinary communication system, what we have understood so far, so there will be an information sequence, right? We are assuming that the voice signal will be converted into digital one by using a digital source, right? Digital, that is analog to digital converter. So I am assuming here the information is available in the forms of zeros and ones, right? So that I will be applying it to the channel encoder. So we all know very well what is the purpose of the channel encoder. So what are the different types of channel encoders also? I think you have discussed or you have studied in your information theory encoding, right? One I can give example of convolutional coding. Okay, and block coding. These are the two most widely used channel encoding techniques. See, what we do in channel coding is we add some controlled amount of bits to the information bits. Yeah, so with that, I will be able to have a reliable communication. Means I can have a reliable communication over the channel. That is the purpose of a channel encoder. Okay, then there will be used to be a modulator, right? And this was absent in the normal communication. What is that? Pseudo-noise sequence generator. So without that, the rest of the blocks are same. So information sequence, we do channel encoding, then we do the modulation, then that modulated signal will be transmitted over the channel. So at the receiver side, so there will be demodulator and channel decoder, then we get back the output. So in case of split spectrum, what are the additional elements are? These two are the additional elements. What are those two? The pseudo-noise sequence generator. Means the information sequence will be passed to the channel encoder. We do the channel encoding technique. Then we do the spreading of the coded signal. Then we do the modulation. Okay, that is the difference. So whatever the pseudo noise code I use at the transmitter side, okay, the same pseudo noise code has to be there at the receiver side. Okay, only that person will be able to detect the transmitted information. Okay, for others it will look like a noise. That is what I stressed in the first slide. Okay, fine. So I think with this you will be able to say, means these two has to be same. Whatever the pseudo noise code I use at the transmitter side, the same pseudo noise code needs to be there at the receiver side. Means the transmitter and receiver should use the same pseudo noise code. Then only it is possible to establish communication between those two people. Okay, for others it becomes a noise, right? So means if X wants to if X wants to communicate with Y, the Y and X should have both the same pseudo noise code. Okay, then only they will be able to have a communication. Otherwise, they cannot. Okay, with this split spectrum communication. Right. So I need not again say. Already I said about channel encoding, right? And I said the preferred technique is what? BPSK for the direct split spectrum system, and FSK is for the frequency of split spectrum. Okay. So that is what here is the stressed. So, so these are the main elements, right? Channel encoder, channel decoder, then modulator and demodulator. These are all the basic elements of any digital communication system. Along with that, the pseudo-noise sequence generator at the transmitter and the receiver is an additional element to the split spectrum communication system. This is what you should take up in this slide. Okay. And as I said, these two pseudo-noise sequence generator has to be identical, right? I think as I said, one will be used at the transmitter side and another one is used at the receiver side. They should be of same sequence. Then only it is possible to establish a communication among them. Okay. Fine. So the synchronization, time synchronization of these pseudo-noise sequence, which is generated at the transmitter side and which is received at the receiver side. So we need to have the time synchronization. That is the challenge, what I can say in this type of modulation or communication system. Okay. So I think in that also I have discussed about that. So what I said, the time synchronization of the pseudo-noise sequence generated at the receiver side, right, with the pseudo-noise sequence contained in the received signal is required. Means whatever the pseudo-noise sequence I use at the transmitter side for spreading the information signal, and then I do modulation, right? Then at the receiver side, what happens? The pseudo-noise sequence will be there, right? And again, on the for demodulation, I use another pseudo-noise sequence, which is same as that of the pseudo-noise sequence which is used at the transmitter side, right? So the time synchronization of those two has to be properly done. Then only I will be able to recover the desired information signal. If there is any misalignment in the time synchronization, then it leads to error. So this is the general block diagram of the spread spectrum communication system. So this much I think you should be able to tell, na? So without these two pseudo noise sequence generator, rest you have said it is a normal or any digital communication system. What is special about spread spectrum communication system? We need to add the pseudo noise sequence generator at the one at the transmitter and one at the receiver side. Even at the transmitter and receiver, where we are going to add this at the modulation point, right? I hope it is clear. Any
Yes,
doubts you
sir.
have?
Yes, sir.
Shreyas, Akshata, what about others? Yeah, you need to see, you can explain in your own words, right, about the information sequence. What we say usually voice, right? Voice is analog in nature, right? That has to be converted into digital by using analog to digital converter, right? So that analog to digital converter will have three steps. One is what? First, I need to do the sampling, right? Then I need to do the quantization. Then I will be doing the coding for each quantized sample. So those three steps together is known as the analog to digital converter, or in simple words, we can say PCM, that is pulse code modulation. So that is how we get the digital data, right? That digital data will be passed through this channel encoder. The moment I say channel encoder, we should be able to visualize the convolutional encoder technique or the block encoding. I hope you have studied, no, those two techniques in your ITC. You remember? Anybody? Say yes or no. Yes,
Yes, sir.
convolution coding or block coding you have studied, no? Studied or not?
Yes,
With
sir.
coding rates. See, convolutional coder with the
Pretty.
coding rate 1 by 3. 1 by 3 means for 1 bit I get 3 bits as output. That is what the coding rate means. So if I reduce the coding rate, so there are certain advantages also and there are some disadvantages also. So ultimately what we need to understand is the purpose of channel encoder is to provide the reliable communication over the channel, right? How do we do that reliability? By adding, means in case of source coding, no? So that block is not shown here, right? Source coding, uh, in source coding what we do, we remove the redundant information bits. Okay, with that we will be able to, we say it is possible to represent the information with bandwidth efficient. But in channel encoding, what we do, we are adding some uh, bits to the information sequence, like CRC, you might have heard that, cyclic redundancy check, right? So by adding those bits, means we say it is under the control of user. That is why we say control redundancy. Okay, so with that I will be able to improve the reliability of the communication. Okay, then I do the modulation technique, right? uh, so as I said, here we use BPSK for direct sequence spread spectrum communication, and for FSK or even MRFSK also for frequency of spread spectrum communication, right? So spreading is also done at this point only at the transmitter side. Then we transmit the signal over the channel. At the receiver side, the reverse process. Okay. So I said the synchronization of the time synchronization of these two sequences, the pseudo sequence, which is received along with the transmit signal, right? And the pseudo sequence, which I use at the receiver side to demodulate, should be synchronized. Then only I will be able to get back the desired information signal properly. Then it will be applied to the channel decoder. See, channel decoder will do the what, reverse process of channel encoding, right? So in channel encoding, I said I am adding some redundant bits. No? Similarly, it will remove those redundant bits and it will extract the desired information bits. Okay. So we say this all these things with respect to mathematical equations. So to say about that, uh, see, I can represent the information bearing baseband signal mathematically by like this. So I think now you will be able to understand this, how I represent V of t. See, V of t is my information bearing signal. Means this is the baseband signal. Okay, so means it is a discrete one only. See, AN is the magnitude of the sample. Okay, so this G T of T minus N into TB is the what? A shifted version of the signal, right? So you can think that it is a discrete information signal, right? This AN indicates the sample value, that is the magnitude, and this one GT of N minus N into GT of T minus N into TB indicates a shifted version of G of T, right? So if I miss, I can vary the value of N from minus to infinity. Na? So for 0, it comes, if I give the value of N as 1, 2, 3, and so on, it will be there on the right side, those samples, right? If I give the value of N as minus 1, minus 2, minus 3, so this will be there on the negative side, that is left side of the horizon. I hope you could visualize this information bearing signal. You take x-axis is the time, okay, and at t equal to 0, let me say one sample, okay. So that is this a suffix n represents, say, if n is 0, a naught, right? So at t equal to 0, I get one sample. Then if I substitute n as 1, so I get the g of t minus tb, right? Means at t equal to tb, I get another sample with a different magnitude, okay. You want me to write and show, or you could visualize that sequence. See, this is summation from minus into infinity. Okay, those are the discrete samples. So how many of you could not visualize this V of t? You can raise your hands. Yes, sir, you are able to visualize that input information sequence, or you want me to write it? Hello, ಯಾರು ಹೇಳ್ತಾ ಇಲ್ಲ, ಮಾತಾಡ್ತಾ ಇಲ್ಲ. Please, Akshata, Shreyas ಹೇಳ್ತಾ ಇದ್ದ. Shreyas ಗೊತ್ತಾಯ್ತೇನಾ?
Yes, sir.
V of t.
Yes, sir.
It is very simple, what I feel, because you take x-axis as a time. Okay, an I said what? Magnitude of the sample, right? You keep substituting the value of n. If I substitute n as 0, I get a naught into g of t, isn't it? So that is one sample at t equal to 0. Then you substitute t as 1. Then what I get? A1 into g of t is 1, right? Means n as 1. So t minus tb means that g of t, whatever is there, that is shifted by one interval, one symbol interval. So I get a signal at that point. Like that, you keep increasing the value of n, 2, 3, 4, and so on up to infinity, we say. Similarly, the negative side also, minus 1, minus 2, minus 3, minus 4, up to minus infinity. So you should visualize an information bearing signal which exists over that interval. Okay. And second one is what I said, the pseudo noise signal. That is what the pseudo noise sequence, right? So this I denoted by C of t, right? Same way. So Cn P of t minus n into Tc. Okay. So these two will be multiplied, right? So output of the product multiplier, right? So output of the product modulator will be what? So that will be what? See, V of t into C of t. That will be my U of t, right? So I can write U of t is equal to, means here I have taken carrier, right? So this is my V of t and C of t into AC cos 2 pi f ct. Okay, right? So this is the general expression what you use to write for modulation, na? AC cos of 2 pi f ct plus theta of t, right? So AC is the magnitude of the or amplitude of the modulated signal, right? And this is the frequency and this is the phase. Okay. So this is the diagram which illustrates how it will spread the signal. Okay, the spreading process I said. No? So this is my information bearing signal. I have taken here only 2 bits. One is 1, another bit is 0. So I have taken, this is the bit interval 0 TB. TB is the bit duration for symbol 1. Okay, similarly for symbol 0 also I can have written this TB here also from here to here. Okay, this is my input signal data V of t, and this is my pseudo noise signal. Okay, See here the pseudo noise signal. I think I have written here what is that sequence, right? So that is 00, 111, 01. Means how many bits it is? 8 bits, na? 2, 4. Is it 8 bits? 2, 3,
7.
5, 6. 7 bits I have taken. Okay. Yeah, 00, 111, 01. Yeah, so this will be multiplied with this. See, how do I get this 0 into here 1? No? So 0 into 1 is 0 only, right? Next bit also 0 into 1 is 0 only. That is why I am getting here 0, 0. Right? So that I represent it with what? Negative magnitude, right? Minus 1. Then here 3 ones are there, right? And here 1 only, right? So 1 into 1 is 1, 1 into 1 is 1, 1 into 1 is 1. That is why I written 1 here with plus 1. The next 0 is there, right? 0 into 1 it is 0. So that is why with negative amplitude. Next 1 is there. So 1 into 1 it is 1. Okay. So this is for symbol 1 from this point to this point it is. Next is what? 0 is there. My information bit is 0. Next again the same pseudo noise sequence will repeat. Okay, 00, 111, 01, right? So for that, if I multiply with this, what I get? 0 into 0, it is 0, right? But here I am representing 0 as what? Minus 1, right? Here also 0 is there, that is also minus 1. Means minus 1 into minus 1. What happens? It is plus 1, right? So that is why represented by plus 1. Next bit also, right? 0 into 0, it is 0. Means I represent 0 by minus 1. That is why it is minus 1 into minus 1 becomes plus 1. So that is why written here plus 1. Next is what? Here plus 1 is there, right? And here it is minus 1. So plus 1 into minus 1, it becomes minus 1. So for another 3 bits, it becomes minus 1 only. Right? I hope is it clear?
Yes, sir.
Yeah. Next bit is 0, no? So that is minus 1. Here also 0. That is minus 1. So minus 1 into minus 1, it becomes plus 1. That is why I written here plus 1. Next last bit is what? Here it is plus 1, right? And here it is minus 1. So plus 1 into minus 1, it is minus 1. So that is why I written is minus 1. I hope this product signal, V of t into C of t, I hope it is clear. One you can write in your notebook and do it. It is easy to understand also. I have taken only the information signal as only 2 bits. One is symbol 1 having a bit interval duration TB and another bit is 0. Okay. And my pseudo noise sequence I have taken here as a 7 bit. What is the 7 bit? 00, 111, 01. Okay. So I here call this one as TC, that is chip duration, I say. Okay, so here the value of n is 7. So it is 7 TC actually. Okay. Is it clear about this multiplication of these two sequences, data and pseudo noise, and how we get this product signal as this? If it is clear, then I will go to the next one. Yes, not hearing from your side. Is
Yes,
it
sir.
clear or still you have any
Yes,
doubts?
sir. Clear, sir.
Yes, sir.
No doubts.
Akshata is responding. What about others? Around 27 people finding. Anup, is it clear, man? Anup? Yes, others should say, na? Gana, Gagana. Is it clear, ma? You understood that multiplication of binary information signal and the pseudo noise sequence? How do we get that product signal? Yes, Gana. Gana illa ansutta. ಬೇರೆಯವ್ರು ಯಾರು ಮಾತಾಡ್ತಾ ಇಲ್ಲ. ತೇಜ ತೇಜ
Yes,
ಅರ್ಥ
sir.
ಆಗಿದೆ?
Yes, sir. Yes, sir. Yes, sir.
ಎಸ್ ಸರ್ ಅಂತಿದ್ದೀರಾ? ಏನು ಕೇಳಿಸ್ತಾ ಇಲ್ಲಪ್ಪ ನಮಗೆ. ಹೇಳಿ ಈಗ ಸ್ವಲ್ಪ ಎಸ್ ಅನ್ನೇ
No doubt, sir.
ನೋಡೋಣ.
No doubt, sir.
ಅಲ್ಲ ಅರ್ಥ ಆದ್ರೆ ಹೇಳಿ, ಅರ್ಥ ಆಗಿಲ್ಲ ಅಂದ್ರೆ ಕೇಳಿ, ತೊಂದರೆ ಇಲ್ಲ. ಪಾಯಿಂಟ್ ಇನ್ ಗೋಯಿಂಗ್ ಹರಿ.
ಅರ್ಥ ಆಯ್ತು ಸರ್. ಅರ್ಥ ಆಯ್ತು.
ಯಾಕಂದ್ರೆ ಇಟ್ ಇಸ್ ಆಲ್ ಸಿಂಪಲ್, ವೆರಿ ಸಿಂಪಲ್ ಟು ಅಂಡರ್ಸ್ಟ್ಯಾಂಡ್. ನೀವು
Yes, sir.
ಸ್ವಲ್ಪ ಯಾಮಾರಿದ್ರೆ ಕಷ್ಟ ಆಗ್ಬಿಡುತ್ತೆ. ಓಕೆ.
Okay.
I hope you will be able to say about this block diagram of spectrum communication. In what way the normal or any conventional digital communication system is different from this communication system. So it should come to your thought, the pseudonoise sequence generator block. Okay. So in normal communication system, these two will not be there. Pseudonoise sequence generator at the transmitter side and pseudonoise sequence generator at the receiver side. So that block will not be there in the normal communication. In case of spread spectrum communication system, that is the presence of pseudonoise sequence generator. So with that, we will be able to, we say, it can provide a more secure communication compared to normal communication system. That is why it has been implemented in the military, later on in civil applications. Okay, fine. Then if this thing is clear, then just it is to show by taking, yeah, this is my information signal, what I represent as a rectangular pulse, okay, which exists from -1 by t to 1 by t. And this is my, the spectrum, means it is in frequency domain. Okay. What I have taken here is in time domain. Actually, this x-axis is time. Okay, here I am showing it in frequency domain. So now x-axis is f. Okay, so this is the spectra of the energy, means information signal, and this is the spectra of the pseudonoise signal. See, the spectra of the pseudonoise signal is much wider than the spectra of the information signal. So when I multiply these two, see, these are the two rectangular pulses, right, of different width. If I multiply, since it is in frequency domain, so their multiplication leads to what? So it is a trapezoidal waveform I get. So it is just convolution only, right? So in case of time domain, we say multiplication of those two signals, right? V of t and C of t. So in frequency domain, it will be convolution of, means the Fourier transform of those two signals will be multiplied, right? I hope you understand this. What is there in time domain and how do we do it in frequency domain? When we do in frequency domain, we take Fourier transform of these two, right? Multiplication in time domain will be what? Fourier transform of their convolution in the frequency domain and vice versa also. So we multiply these two, we get this signal. This is what the spectrum of the combined signal. Okay. Yes, sir. So for that, see what is added for this one, it is -1 by t is my information signal, right? It exists from -1 by t to 1 by t. And my pseudonoise signal exists from what? -1 by tc to 1 by tc. So when I multiply these two, I need to write the duration, right? Minus of this 1 by t plus 1 by tc, means it's -1 by t minus 1 by tc, negative side. And positive side, it will be what? 1 by t plus 1 by tc. That is why I written here 1 by t plus 1 by tc. Clear about writing the limits?
Yes, sir.
So this is all about the transmitter side. So at the receiver side, what means, how do we do the demodulation, right? This is the what I say, direct sequences from demodulator. So you are aware of this correlator, right? Multiplier followed by an integrator is a correlator. So this function you understand. See, what is the first part? See, R of t is the received signal, I say. Okay. So R of t is my received signal at the receiver side. That I need to multiply first with the what? Pseudonoise code. That is a first step, right? After multiplying the pseudonoise code, then it will be passed through the demodulator circuit. So that is a correlator circuit, right? So at the correlator, one input to this one is what? That GT of the cos 2 coefficient. This is the carrier signal, right? Then I get output here. That will be sampled. Okay, the sampling circuit will be there. So even that has to be synchronized with its clock. Then output of the sampler will be given to the decoder. So actually it is a decoder. Okay, is a decoder. So that decoder will do the decoding of the received information sequence. Means we will take a decision whether, depending upon the magnitude, whether the received symbol is 1 or 0. That's what the thing happening, right? Yeah, see how there is a link. Means I need not stress much upon again correlator, what correlator will do and other things, right? So that is what, if you already have studied about this receiver part, here in your own words only you can say how does it do the demodulation. The difference only thing is, first you need to write this block. What the received signal has to be multiplied with the pseudo noise code. That is the first thing. If we miss out this and if we go directly to the correlator part, then it will be a different thing, right? So only uh, after multiplying the received signal by the pseudo noise code, then only it is possible to do the demodulation. Otherwise, it will be a error signal. Means the decoder will not be able to detect the desired information signal. Yeah. So these are the some terms which we have used in this one. Means to say, see the information, right? We can say the information rate to the encoder is, means channel encoder, at what rate we apply the information bits. We generally we rate it is R bits per second. Okay, and we say the available channel bandwidth is W hertz. Okay, and we are all aware bit rate and the what RB is equal to what 1 by TB used to say, right? So RB is the bit rate and TB is the bit duration, and they are reciprocal to each other. That is what is said here. Reciprocal of R. R is a bit rate, I can say. So is denoted by TB. So TB is equal to 1 by RB or R, anything. Okay. So that will define what? The pulse, that is the duration of the pulse, right, corresponding to the transmission time of the information bits. Means TB is the bit duration, right? So if I know at what rate I am feeding the data to the channel encoder, if I know the bit rate, I will be able to calculate the bit duration. That's what the meaning. And I am assuming the pseudo noise code is at what rate? W times per second. Okay. So reciprocal of that will give you the chip duration. The chip duration is the what? That is the duration of the pseudo noise one pulse. Okay. So I call that as chip interval, right? So W by R, W means that I call as a bandwidth expansion factor. Okay, fine. So that is why I denoted that by B suffix E as the bandwidth expansion factor, which is equal to W by R. So here, what I said, W is 1 by TC, right? W is 1 by TC, which is what? Reciprocal of the chip duration of the pseudo noise code. And R I said 1 by TB. So if I substitute that in this expression, I can write that as TB by TC, because see, R is what? 1 by TB and W is 1 by TC, right? So 1 by TC divided by 1 by TB can be written as what? TB by TC. I hope this is clear. Or you want me to write that expression here? See, I said bandwidth expansion factor, which is equal to what? We say W by R. Okay. So it is defined like that. Bandwidth expansion factor is defined as W by R. What is W? W is 1 by TC. Right. So with this I am saying reciprocal of the W denoted by TC means W is equal to 1 by TC, I can say. What is this TC? Is the chip interval of the pseudo noise code, right? And R is what? It is 1 by TB. Right. So 1 by TC divided by 1 by TB can be rewritten as what? TB by TC. Okay. So we say in practical system, this ratio TB by TC has to be an integer. Okay. And we call this TB by TC as the uh, what? The number of chips of the pseudo noise sequence per information bit. Means see, TB is the what bit interval, right? Or bit duration. That is the information bit duration, and TC is the chip interval, right? So TB by TC, that will give you the number of chips, okay, of the pseudo noise sequence per information bit. So as per this, so whatever the example I have taken here, so with respect to this, will you be able to say that ratio TB by TC? Anyone? Here, what is the value of TC? How many chip intervals are there? So expect answer. Yes, you could understand my question. I said W is equal to TB by TC, and which is also equal to what? LE, that is length of the pseudonym sequence, right? Which is equal to TB by TC. So here TB is what? 1 bit information, right? That is a bit duration. Yeah, and TC, how many chip intervals I have here? Totally 7.
7.
Yeah, so 1 by 7 is the, for every 1 bit of information, I'm using 7 chips of pseudonym sequence. That is what the meaning is. Okay, this is see number of chips of pseudonym sequence per information bit. Is it clear now this point? Number of chips of pseudonym sequence, okay, per information bit is what LE. I should do this. Yes, this point is clear. TB
Yes,
is the
sir.
bit
Yes, sir.
duration and TC is the chip interval. With the example what I have taken here, see this is my 1 bit duration, right? That I am using 7 bits of pseudonym sequence. So 1 by 7 will give you me the value of this. What is that? LE. Okay. Fine. So means I am expanding 1 bit into 7 bits. That is what the meaning is. Right? 1 by 7 means I am spreading my information bit, which is having a duration of TB, into what? Into 7 chips. Right? 7 pieces. I am doing it into 7 pieces. Then I am transmitting by modulating over the air. So at the receiver side, if I have the same pseudo noise sequence, then only if I multiply it again back, means if I do a de-spreading process, then if I do demodulation, I will be able to get back the information signal. That's what the meaning is. That is why I said only the intended receiver will be able to recover that signal. For others, it becomes a noise. Okay. So here means at the receiver side, right? Again, I will be multiplying it by carrier. So at the transmitter side, I written VC, AC, VT, C of t into cos 2 pi of CT. You know, again, I am multiplying C of t at the receiver side. So it becomes C square of t. So we know that the value of C square of t is 1 for all the values of t. How do we say C square of t is equal to 1? Anyone can say C square of t. Looking at this diagram, this is my C of t, right? What is the square of this? Its magnitude is +1 and -1. See, C of t is 1 now, whether for it is for symbol 1 it is 1, for symbol 0 it is -1, right? See, -1 into -1, if I take C of t as 0, 0, so -1 into -1, again it becomes +1 only. Or if I take 1, 1 also, it is +1 into +1, again it becomes +1 only. In that sense, I am saying C square of t is equal to 1 for all the values of t. Clear. So with that, I can write AC into V of t into cos 2 pi f CT. Okay. So this AC V of t cos 2 pi f CT, okay, occupies a bandwidth of what, R hertz, which is what the bandwidth of the information bearing signal is. So this is just about a brief understanding about the direct sequence spectrum and as well as the block diagram of the spectrum communication system. So, if you have any questions, you can ask me. Let me, if you want, I can take up next topic in continuation with this, or I can take up next class also. Yes, is it worth of? I did.
Yes, sir.
Is it okay?
Yes, sir.
You
Yes,
could
sir.
understand what. So then, how are you, ma?
I'm fine, sir.
Fine, fine. Yes, 9 charts. So, yeah. Yes, enter your question in the chat box.